Greetings, calculus students, and welcome to the lesson on inverse functions. And in this video, we're going to take a look at inverse functions, of course, and their derivatives, and how the derivative of the inverse function is related to the derivative of the original function. So let's begin. Just a quick review of inverses. So from a function machine perspective, you basically have this machine f of x, you feed in x and you get out some number y, for example, and then the inverse would just be, let's say I have something here called f inverse. Well, all that really does is it takes y, whatever that value was, and then it reverses that direction, and now instead you get x. Okay, so this is essentially what it means. You plug in a number, you get the output, and the inverse does the exact opposite. Whatever was the output now becomes the input. So let's look at a numerical example of this and see how the inverse is related to its original function. Okay, so let's say I have a function where if I were to feed in 1, it gives me 3, feed in 2, it gives me 8, and so on. Well then, what would the graph look like for this? What would it look like if I gave a plot of the input and the output of the inverse? Well, it's just the opposite of this. So the output is now the input. So instead of passing in 1 and getting 3, I'm going to pass in 3 and get 1. Okay, so all of these are just reversed. Okay, so numerically, what this really does is just swap x and y. Okay, x being the input and y being the output. So this is input, and then this is output. Okay, that's essentially what inverse functions mean numerically. Well, what about graphically? So if I were to graph this, if I were to graph these numbers 1, 3, 2, 8, 5, 3, 4, 5, 7. Okay, so these blue dots here represent f of x, and then I were to graph f of negative 1 or f inverse. Well, now I graph 3, 1, 8, 2, and then 7, 5. And you can see that there is a little bit of a symmetry here. If I drew it better, you could see it better, but nevertheless, we could see it. And the symmetry here is that it is reflected over the y equals x line. Okay, so there's a symmetry between these points here over the y equals x line. Right? So I'm going through this pretty fast because I'm assuming you already know most of this stuff regarding the function machine, the numerical value, and the graphical value. So this is symmetric over the y equals x line. Okay. So let's keep going, and let's see just a couple facts here regarding functions and its inverse. So one thing that we do know is that if you take f and you compose it with f inverse, then you should get x again. Okay. So in other words, this is saying, like, I have a function f of x, okay, and x goes in and then something else goes out. Well, f inverse, it does the exact opposite. Y goes in and x goes out. So now if I take a value and I pass it into the inverse first, okay, I'm going to get a result. And then if I take that result and I pass it into the original function, I get back to where I started from. Okay. Sorry, so I may not have written this very well. Maybe I should say f inverse of f of x. Okay. So let's say I have f of x inverse here. I take y and I have f of x here. I take x and I pass it into the function, and I get y. And then I take that result and I pass it into f inverse, and now I get x again. Okay. Now, if we do it the other direction, the other composition, this is also true. Okay. Now, I'll make a note here. There may be some restrictions, and we'll talk about restrictions in just a little bit, in a couple minutes. In this video, we'll talk about what some of these restrictions are. But generally, these two facts are true. and they're not really theorems. There's facts. They are almost like definitions. Okay, so it depends on how you define an inverse. Okay, if you define it in terms of the function machine or graphically up here, then this is a theorem. But you could also define it this way, and all this information up here would be like the theorem. Alright, so one more topic in this video, which is when does f even have an inverse? So let me give you an example. Let's say that we have something like, oh, I don't know, the very familiar quadratic f of x equals x squared. Okay, does this have an inverse? Well, we could look at this from a table perspective and say, if I were to pass in 1, no, let's do something more interesting, 2, I would get 2 squared, which is 4. If I pass in -2, I would get -2 squared, which is also 4. Well, now what is the inverse going to look like? Okay. So if I pass in 4, then I get 2, and if I pass in 4 again, then I also get -2. And this presents a problem because this is not a function, not a function. Okay. Since you have the same input and you're getting 2 different outputs. Okay. So the inverse of this function, f inverse, is in fact the square root of x. However, the restriction here is that x has to be positive, okay, or equal to 0. So if we were to take this function, this graph, and reflect it over the y equals x line, we would get this picture. Right? But we know this is not a function because it fails the vertical line test, this red graph that I've drawn here. So we give this the restriction that it only works, okay, that this function here is only a function, or this inverse here is only the inverse of the original function whenever x is a positive number. In other words, we choose to ignore part of the original graph and just say, well, the rules of the inverse here apply only when x is a positive number. So this is what I mean by up here when we said that there may be some restrictions. Alrighty, well, we're going to end this video here, start another one that deals with some further details about inverse and inverse functions.